Hi, I'm Wen Canzhang, a PhD student from the UBCAM lab at National University of Singapore. Here I'm glad to share a paper, Debiased-CAM to mitigate image perturbations with faithful visual explanations of machine learning. AI can recognize an object from an image and generate a saliency map as explanation. Look at this example using Debiased-CAM, a common saliency map approach to explain where the model looks at when labeling the photo as fish. When working on clean images, we consider the saliency map as unbiased, since it can highlight correct pixels, which enhances the model's transparency and improves human trust. So far, so good. However, when images are distorted, such as under image blur, although the model can still recognize fish, the saliency map becomes deviated and misleading by highlighting the man's face area, and we consider it as biased-CAM. We solve this problem with Debiased-CAM, a self-supervised training approach that helps the CNN model to generate less deviated explanations on distorted images. The world we live in is not perfect, where distortion, corruption, or perturbation happens in data, such as an image blurred with a privacy protection scheme, with a wrong color temperature due to camera missettings, or with varied daylight conditions. Here, to discuss them in a unified way, we consider all these non-perfect images as biased. Now let me show how our technical approach works. A CNN model trained with clean images can produce more meaningful saliency maps, or so-called unbiased CAMs. However, when querying with blurred images, this model not only has the chance to predict wrongly, but also generates deviated saliency maps, or biased CAMs, that highlight irrelevant pixels. One naive solution is by fine-tuning the model on blurred images as augmented data. Although calibrating the prediction, this still suffers from producing deviated saliency maps, since the training process is not aware of explanation. To fix this issue, we explicitly formulate the saliency map generation as a secondary prediction task. We leverage the information from unbiased CAMs and construct a self-supervised learning task to help the model generate debiased CAMs on blurred images, which are similar to unbiased saliency maps. Our approach also supports a more realistic multi-biased setting, where training images are augmented to different blur bias levels, and the model needs to predict that information as the third task. Bringing all these features together, we designed a multitask, multi-bias architecture. Let's see how much CAMs are distorted and how well Debiased-CAM can help. We evaluated for different prediction tasks, image classification and image captioning, and different bias types, including synthesized biases such as image blur, color temperature shift, and natural bias such as day-to-night light change. Across these, image bias leads to CAM distortions. Relative to unbiased CAM, we see that biased CAM becomes very misleading. This is still problematic if we only fine-tune the CNN model on biased images with their labels. Fortunately, Debiased-CAM can recover the explanation faithfully, which means even for strongly biased images, Debiased CAMs are similar to unbiased CAMs. As can be seen here, when testing with the base model, both the prediction performance and the explanation faithfulness degrade with the increasing bias level. Fine-tuning the model with simple data augmentation can hardly handle this issue, especially for saliency map faithfulness. In contrast, our debiased training approach can improve both the prediction performance and the explanation faithfulness, no matter under single bias or multi-bias settings. And our approach can achieve more faithful explanations for different prediction tasks and bias types. Next, we explored how sensitive are people to biased CAMs and are Debiased-CAMs good enough in user studies with an image label verification task. We objectively measured saliency map truthfulness with a grid selection question. Here we considered a saliency map to be truthful if the highlighted areas were consistent with humans' grid selection opinion. Then we show participants a blurred image with different machine-generated saliency maps and asked them to give subjective ratings. We launched the study with 32 participants recruited from the Amazon Mechanical Turk platform. We found that although saliency map truthfulness degraded with the increasing bias level, Debiased-CAM could always improve the truthfulness. We also measured whether participants consider the saliency map helpful in image label verification. Instead of a common multiple choice question, we used the balls and beans question to elicit the answer as a probability distribution. This allows us to measure the participant's confidence of the correct label, even if her most likely choice is wrong. We collected the subjective helpfulness rating on saliency map in a study with 162 participants. The result indicates that, although all CAM variants do not help people label heavily blurred images, and biased CAMs tend to degrade helpfulness, Debiased-CAM can significantly improve the user's decision performance on moderately blurred images. And users generally consider the Debiased-CAM more helpful in labeling regardless of the blur intensity. By analyzing participants' rationales, we found that participants consider saliency maps more truthful or representative because the highlighted regions have accurate size and shape, or captured more semantically relevant cues. They would consider the saliency map helpful for recognizing a blurry image, since it helped focus humans' attention or provided hints, benefiting the process to form hypotheses and confirm suspected objects. To sum up, we identified that the contextual bias in image may cause misleading explanations. We provided a self-supervised approach to achieve debiased explanations, and we designed sensitive measures for saliency map explanations and found various advantages. Please check our paper for more details. Thanks for listening, and I'm glad to take questions.